Okay, let's take a look at some more equations with some algebra. So first we're going to introduce sine x plus sine x is equal to 2 sine x. 2 sine x. In the notes, 5 cos x minus 3 cos x is 2 cos x, adding and subtracting like terms. So what if I have an equation like 3 tan x equals 5 plus tan x? Well, that's difficult for me, so I'm going to make m equal to tan x. And I'm going to put a box around that so I don't forget to put it back in later. And I'm going to make the equation 3m equals 5 plus m. Then I'm going to solve that. So I'm going to subtract m from both sides. So 2m equals 5. Then I'm going to divide both sides by 2 and get m equals 2.5. Could have left it as a fraction, whatever. And you guessed it, dot, dot, dot. Put tan back in for m. Solve it with previous methods. Tan's positive. 2 triangles where tan's positive. Do the inverse calculation. Second tan on the calculator. Give it your reference angle. Put the reference angle in both locations. Put your arrows in. And then figure out what x is equal to. Remember, if they give you a domain or a period chain or a domain, make sure you act accordingly. Okay, let's take a look at an example down below. Cos x over cos x plus 1 equals negative 1 over 3. Well, that's really weird looking, but what if I decided to make m the funny looking thing, cos x, and make sure I put box around it? Because I don't want to forget to substitute it back in at the end. Excuse me. So m over m plus 1 equals negative 1 over 3. And in the notes you can see that I've times those sides by 3. So 3m equals, and I've times those sides by m plus 1. And if I distribute the negative, I get negative m minus 1. Feel free to try that on your own with multiple steps and make sure you get there. So what will I do with that? Well, I'm going to add m to both sides, so I get 4m equals negative 1. And then I'm going to divide both sides by 4, and I get negative 1 over 4. And you guessed it, dot, dot, dot. I'm going to put cos back in for m, and then cos x is equal to negative 1/4. And then I'm going to draw an ASTC graph, and I'm going to put 2 triangles where cosine's negative. Then I'm going to label the triangles according to SOHCAHTOA. And then I'm going to inverse the positive on my calculator and get the answer, which would be the reference angles. And then I'm going to put my arrows in, which are the angles in standard position. And then I'm going to figure out what my arrows are worth. So let's take a look at a few examples down below. Just going to shrink that up a little bit. I hope you're not writing as big as I am. Oh, excuse me. Let's go off to the right for a second. This one's going to be quick. 2 sine x equals 4. Well, if I divide both sides by 2, sine x equals 2. And I know that sine can't equal 2, so that has no solution. Sine can't be outside of 1 and negative 1 on the number line. This is another interesting little one. I'm just going to do it off to the right. It's inside a box. Sine x equals cos x. Well, that's weird. We can type it in our graphing calculator, y1 equals y2, and figure out the answer. But I can divide both sides by cos x. And if I divide both sides by cos x, I get on the left-hand side sine x over cos x. And on the right-hand side, if I divide both sides by cos x divided by cos x is simply 1. And I know from previous sections and from my formula sheets that the definition of sine theta, or sine x over tan x, sine x over cos x is just simply tan x. And tan theta equals 1. Dot, dot, dot. 2 triangles where tan's positive. ASTC, special triangles, reference angles, arrows, etc. Let's shrinken those guys up a tad. Okay, so Let's take a look at example down below. 5 minus 2 cosecant x equals 0. Well, I know that from my definitions, cosecant x, or theta, is equal to 1 over sine x. Remember, the first letters switch, or the first letters are the reciprocals of each other. So I can simply substitute 5 minus 2, and for cosecant x, I can say times 1 over sine x equals 0. Well, now my funny looking thing is sine x, so I'm going to make m equal to sine x. Excuse me, I'm always going to box my stuff. So I did box that equation. That's a formula from our formula sheet and our methods that we're going to do off to the right. So if I put m in for sine, I get 5 minus 2 times 1 over m equals 0, or simply 5 minus 2 over m equals 0 as seen in the notes. So I can simply add 2 over m to both sides, so 5 equals 2 over m. And then I can cross multiply, therefore m will be 2 divided by 5, or simply 0.4. And you guessed it, dot, dot, dot. Put sine back in for m. Sine x equals 0.4. 2 triangles where sine's positive. It's not a special triangle, so we have to use the inverse calculation. Second sine positive, always inversing positive, 0.4 equals whatever it is. That's our reference angle. Then put that into our reference angle, into our ASTC graph with our 2 triangles where sine's positive, and then put our arrows in and figure out what our value of x is. Excuse me. There is one more example off to the right, further using m, and that one we actually had to factor in the end. And look at that, 2 more dot, dot, dots. If you ever see dot, 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 it means you've done this before, you know how to do it. Go back in your notes and figure it out. Okay, factoring and distribution. Let's start off with something like cos x, open bracket, cos x plus 1. Well, if I wanted to make m cos x, and then I wanted to write it out a little bit simpler, I could say m open bracket m plus 1. If I made m cos x, I'm not going to do it every single time and think through it in my head. I'm just going to think this. I'm going to think distribute the m. I'm going to think m squared plus m. And that would be my answer. So now I'm going to work with that off to the left. Well, cos x times cos x, we actually write cos. I'm going to do that line down because we actually have to write something named cos squared x. That's where the squared goes. It's not x squared, it's cos squared of x, which is cos x times cos x. And then if I distribute further, I get cos x times 1 is just simply cos x. And I just distributed. But I'm not going to circle that answer. It is circled in your notes, but in big red here, we need to know that we need to be able to go back and forth, just like we could over here. Distribute or remove a greatest common factor. So now let's see an example with sine where I remove a greatest common factor. So sine x minus sine squared x. Well, off to the right, maybe I'll use a different letter this time, so I'll write n minus n squared. I'll factor out an n, and I'll be left with this. So I can simply factor out a sine x, and I'm left with 1 minus sine x. And again, I'm not going to circle either answer. We want to be very familiar going back and forth in both directions, factoring, distributing, etc. Off to the right, let's do that example down below, but if you're looking in your notes, it's off to the right. So that's sine x, cos x, plus cos x. Well, we made cos x m earlier, and we just made sine n, so let's stick with that. So that would be n m plus m. Now, they both have an m, so I can factor out an m, and I get n plus 1. So, off to the left, they both have a cosine, so I can factor out a cosine, and I get sine x plus 1. So, if doing these things off to the right helps, feel free, keep doing it. If it doesn't and you just want to go at it, do that. Okay, the next one in the notes is cos x plus 1 cos x minus 2. Well, off to the right, what do we make? We're going with m. The notes may not be perfect. I may accidentally use the wrong letter, but I think it's m. Yeah, it's m over there. It's m above. Yeah, let's go with m. So that's just m plus 1 times m minus 2. And that shouldn't be difficult. We know how to expand using firsts, outsides, insides, lasts, or a mnemonic device foil. So I'll write that answer down below, m squared. Now I'm going to do the middle term in my head. Negative 2m plus m is minus m, and positive 1 times negative 2 is negative 2. So back to the left. That would be cos, remember, squared x minus cos x minus 2. And again, I'm not going to circle my answer because I need to know that I'm going to go back and forth. I circled my answer kind of in the notes because you kind of want to see like a difference between questions, but I'm just using lines here. So again, off to the right, we want to be able to go back and forth between each one of these factoring or distribution types all the time, all over the place. So down below or down off to the right, you see more interesting types of factoring, differences of squares. Let's take a look at that one. So off to the right, actually, off to the right is just a different example similar to the last one. Let's go to the next line. 1 minus sine squared x. 1 minus sine squared x. So, well, what does that look like? Well, that's a 1 minus, I used a different letter in the notes just for fun, a squared. Well, that factors to be 1 minus a, 1 plus a. Differences of squares. So this factors to be 1 minus sine x, 1 plus sine x. I'll put in a little vertical bar there. So lots of differences of squares examples. Off to the right is an example of m to the 4 minus n to the 4, which is m squared plus n squared, and m squared minus n squared. And then the one on the right factors again. So that's m squared plus n squared and m plus n, m minus n. And that one gets really complicated. So more examples down below, different types of factoring. Be really, really comfortable with factoring trinomials, factoring them all sorts of different forms. It always helps to use different letters off to the right. Bring it back to grade 10. Figure it out. Couple examples at the bottom. Rearrange the order of the terms. We're not going to go over that. A plus B equals B plus A. Don't forget about your negatives, etc. Lots of simplification. Okay, let's take where we started from last time. Let's take cos squared x, just in the last sheet in the video, plus cos x equals 0. And in the notes, I've made m cos x, and I've done all those steps, and I'm just not this time. So I'm going to factor out a cos. Cos x, open bracket, cos x plus 1 equals 0. And then I remember, if I have two things being multiplied together to make 0, a principle from grade 11, AB equals 0, that means that either A is 0 and or B is 0. So I set my factors equal to 0 separately and solve. And you know what's coming, dot, 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 dot. So cos x is the x value of the unit circle. That's when it gets confusing, because lots of times it helps to say cos theta. is the x value, because sometimes they use x as the angle interchange for theta, so that one's confusing. But cos is the x value of the unit circle. Where's the x value 0? Well, it's here and here at pi over 2 and 3 pi over 2. So x equals pi over 2, and sometimes I'm going to use commas. And then this equation is cos x equals -1, and then cos is the x value of the unit circle, and the x value of the unit circle is -1 at pi. Therefore, the answer to that one is x equals pi. Notice it only has one answer. So I've done a lot of examples down below with different types of factoring, etc. The first one, we made m sine x. It's a nice and simple one. The second one, we made m sine x again. The third one, we made m cos x. The first one, we rejected the -2 because sine can't be -2. And then we got some other answers through ... And then we did a more difficult factoring off to the right. And again, there's some more ... And the example down at the bottom is interesting because we get to answers with decimals. I'm just going to write one of them down actually at the bottom of the page. Cos x equals -0.52. And that's a ... 2. But where did it come from? Where did that answer come from? Excuse me, m equals whichever. Well, notice off to the right, quad form, like nothing stopping us from factoring using quad form or any other type of method that we've done before. So be careful with those factorings. They are interesting. But same principles as we did on the page before. I introduced a whole bunch of factoring techniques. Then it's just a matter of applying the AB equals 0 principle from grade 11, setting our factors equal to 0 separately, ... Use your knowledge from before to solve those. Always check with your calculator, and just don't forget about the factoring type quad form, because that one could come get you. Okay, identities. So let's take an example like sine 2x plus cos x is equal to 0. And I'm going to shrink that up a tad and move it off to the left a little bit. So what is this? Well, we've seen this tiny little 2 before with the period change, but this is a little bit of an overlap between chapters ahead of here called trig identities for public schools who use the textbook for now, at least in 2019. That we don't do this until 2 chapters from now, and then they introduce this after, but because we've done so much factoring, I think it's better to introduce it now. So on our identity sheet, we have a definition. Sine 2x is equal to 2 sine x cos x. I'm going to put a box around that because it's a definition. And that's from our formula sheet given to us in a few chapters. But sometimes if you want to get ahead, it's just a lot of fun, because if this factoring and solving has been in our heads with all the ASTC and everything, very helpful. So I'm going to replace sine 2x with the definition off to the right. So this sine 2x turns into be 2 sine x cos x plus cos x from above equals 0. Now look at that, they both have a cosine, so I can factor out a cosine. So cosine x, open bracket, 2 sine x plus 1. Check by distribution, it's good. Two things equal to 0, set them both equal to 0 separately, as we've seen in the past. And 2 sine x plus 1 equals 0. Let's solve this one first. Excuse me, lots of times I'm going to say 2 sine, and what I mean is 2 sine x. Always sine x. I might say sine squared and forget the x, etc. 2 sine x plus 1 equals 0. Sine x, therefore, equals -1/2. And what do we have here? We have a ... and another ... And I'm not even going to write those solutions down. Feel free to try those on your own at home. So I'm just going to shrink this up a tad. Excuse me, I lost a 2 in the process. I'm going to move it to where it needs to be. Okay, so now let's do another question. So let's go for sine x minus cos squared x minus 1 equals 0. Well, I know I'm going to shrink that up a tad. I have to write another definition off to the right. So I know that from my formula sheet, seen in the formulas in the trig identities chapter, has all of the identities on the front page and then a lot of useful algebra on the next page. And one of those is that cos squared theta is equal to 1 minus sine squared theta. And that's a definition, so I'm going to put a box around it, and I'm going to substitute with brackets. So we have sine x minus open bracket, and for cos squared, I'm going to put the definition off to the right, 1 minus sine squared theta minus 1 equals 0. And then I can distribute the negative, and I get sine x minus 1 plus sine squared theta minus 1 equals 0. And then I can rearrange the order of the terms and combine like terms. So I have sine squared theta, x. The definition off to the right is theta, but if we're using x, we have to use x. So again, down below, x. They're all x. Rearranging the order of the terms, sine squared x plus sine x minus 2 equals 0. You guessed it, ... So the big key is deciding off to the right, big red at the top, which definition to use and why. So the first one, we used that one because that's the information we had. The second one, we used that one so we could get it all into sine squareds. So there is a whole bunch more examples on this page. Let's just do one more. So let's shrink this up a tad. And let's go for sine x plus cos 2x equals 0. And I'm always running out of room, so I got to horizontally shrink it a little bit. It's easy to write it big and shrink it. And I have another identity, and that identity is cos 2x equal to a multitude of things. So if you've already printed off your sheet and you want to highlight them, go ahead, but it's equal to 1 minus 2 sine squared theta. The definition we should usually write in theta. I erased cos 2x and I wrote cos 2 theta. I'm going to put a box in red around that definition. So I can substitute that for this. And even if there is a plus sign in front, sine x plus open bracket 1 minus 2 sine squared x equals 0. Substituting the definition off to the right. And then feel free to distribute the negative and rearrange the order of the terms as we did above. And then you guessed it, ... We should be able to solve all these. Keep in mind, these tricks are going to be really good for trig identities when we do them in the future. So come back and review these different identities. There's a couple more examples on that page, but we don't have all year.